Hi everyone, how are you? I'm very happy that I would like to welcome you to the first session of the Drug Delivery System podcast series. So this series is basically part of the course in Pharmaceutical Sciences in the Faculty of Pharmacy, Universitas Gadjah Mada. And before we start, let me first introduce myself. My name is Adiat Mika. I'm a lecturer and researcher from the Laboratory of Physical Pharmacy and Biopharmaceutics. And today I'm very happy that I am with my colleague, Dr. Ronnie Martin. He is the staff in the Laboratory of Pharmaceutical Technology in the same department as mine, in the Department of Pharmaceutics, Faculty of Pharmacy.
Yes,
Welcome,
yes.
Dr. Ronnie. But actually, that is not my best reason that I'm very happy you are here. My most reason that that I'm very happy that you are here is because I know that you have been doing a lot of research in nanotechnology, and
sure.
that is the most exciting part that I know from you. And then actually, it's not only the research itself. I know some products that's already been born from your laboratory. I know you have food preservatives. I know fertilizer from your laboratory. And actually, what interesting is that all of your products there, I can find the tag. It is with the nanotechnology.
Nanotechnology, yes,
yeah.
correct.
Well, actually, I would like to ask first, what is actually nanotechnology?
Okay, nano is not like a candy, you know. We know about now nano is like candies. From the word of nano, it means like the size. So nanoparticles mean, or nanotechnologies mean like technology in nano size or particle in nano size. And when we think about nano, is like smaller than micro, you know.
Okay. Yeah.
Micro is like one micro is like 1,000 nano. So it is less than micro for sure. So when we talk about nanoparticles, we talk about particle in nano size. So it's the matters about size actually.
Yeah. Okay. So in general, nanotechnology is all the technology of the
size.
particle
Yes,
in the nano size.
It's nano size.
Okay. So is it true that if people say that the special things about nanotechnology is because it is the smallest particle exists, for example?
I mean, yeah. When we start, maybe we can think about micro first, because nano is, like I said before, smaller than micro.
Mm-hmm.
In some years ago, when we talk about micro, maybe we cannot see the micro. When we found microscope, and then we can see
the
micro size.
Yes.
Because of the device or microscope, we can see exactly the size of micro. Nano is, I think, when we talk about nano, is already exists, because when we see from the history is, I think before BC, before the years before Christ in Egypt, they found gold solution of gold. They say gold that dissolve in water.
Yeah. Okay.
Dissolve. I mean, now we can see disperse.
Yes.
Because we have transmitted electron microscope to see,
and then we can see, we can confirm that.
But
it's a
at that days,
yes.
I think because this disperse or dissolve, when we see with our size, is the same. I mean, like, we cannot distinguish exactly between dissolve and disperse. But with advanced technology now, with transmitted electron microscope, we can really not just see but characterize the size. So we can say that this is nano, smallest than micro. So I'm saying, like, human can create, but just discover.
Yes, of course.
So I mean, like creation is like God jobs, not our jobs here.
Yeah. Of course, it's interesting. Yeah, in the past, not just because it's not. We cannot confirm that it exists. It's already there, so people just say it's a solution. But nowadays we know that it's dispersion.
Dispersion,
okay. Okay, so but in terms, for example, in the application of the nanotechnology, I don't know, because your products contains this nanotechnology. But my question is that always the best solution for everything, or it has to be only in a particular cases, not for everything that you have to be, it can be solved by nanotechnology?
Yeah, I mean, nanotechnology is like tools.
Yeah.
So it's like if we have a problem, we can solve the problem with some tools or some method, for example. So nano is just one of the method that can dissolve the problem. For example, maybe we can see from the computer technology. 10 years ago, maybe we have micro technology with silicon nanotechnology, micro technology, so we can create computer smaller. But now with nanotechnology, we can convert the desktop computer become this.
Yeah, something
so it's like
that small.
Of course, smaller mean more effective. Smaller mean they can connect closely. So the transistor, everything is closely, and then it's easy to manage.
Yeah.
But not always smallest and better or the best, but depend on your problem. For example, for the drug. When we see the drug now, when we can see the condition of how we treat human with the drug, the dose of the drug is getting higher, right?
Yeah.
Because now when we say about paracetamol, for example, in the market we have 600 microgram.
When they call it 40.
Okay, 40. It's like crazy because nowadays we just have 150 milligram of drug in one tablet. They will increase because, of course, the aim of the higher dose is because they need to increase the effectivity. But is it good or not?
Yeah, that's right.
So, at that cases, nanotechnology may be one of the method or application that can decrease the dose because smalls, smalls, and then it can enter easily to the cell or with paracellular or transcellular is smaller because nano mean smaller than micro. When we talk about micro, is the cell, so it's easy to enter the cell or with endocytosis, and the exocytosis is easy.
Yeah.
So it's not always like that. Depend on the class of the drug. For example, we have class 1, 2, 3, 4. I mean
the pharmaceutics sugar system. Yes. Yes, it's interesting since you mentioned the application for the pharmaceutics use. Because, for example, if we only see the drug as molecules, then of course the size itself is already
small.
Okay.
Yes.
But the problem is that, of course, if we want to see this drug, for example, paracetamol in the form of molecules, then we need maybe organics. We need to put the drugs into organic solutions, right? Yeah. And then, the problem is that it's not always suitable for us because we need, polar system to make everything not toxic for us. And then if we want that to work, then as you mentioned, we need to increase the dose. But of course, increasing the dose is not only increasing the pharmacological effect, but it's also increasing the potential of the toxicology. And then you mentioned that this nanotechnology can help.
Yes.
What's interesting is that So for these drug molecules, we can create an engineered particle, right? It's not becomes that it's only the only molecule that we transfer into our body, but we engineer it, for example, with I don't know. Can you maybe tell us about what kind of materials can be used to produce these
maybe I will explain a little bit about the advantages of nanoparticle. It means like in general smallest is better in general, but not always. But when we talk about nanoparticle, especially in life science, especially more in the drug or in the pharmacy industries, first we have a problem with solubility. It means because when we have a drug and then we eat the drug orally, and then the drug maybe will be escape from the tablet or from the capsule, and then they meet the water, and then if the drug doesn't like water, they will precipitate. This is the problem of the dissolution, isn't it? So if your drug doesn't have good dissolution properties, bioavailability also have a problem.
Of course.
So first we have advantages of nanoparticles about how to increase the properties of dissolution. We have problem with class 2 and 4. Even maybe in class 2 they don't have problem with absorption, but absorption is next step after dissolution. So solubility should be, we have to increase it, or not solubility, but maybe in terms of dissolution. The second is about stability. Of course, some drug doesn't have problem with solubility, but for example, in our GI tract or gastrointestinal tract, we have a lot of barrier. For example, acidic barrier in the gut, or enzymatic barrier in the GI, in the intestinal, or everything. So the technology of nanoparticle in the life science, especially for the drug delivery, is encapsulated. So the drug and will be combined with some polymer, for example, with biopolymer or polymer that you have, and then they can encapsulate the drug. So it means like when you make a capsule but in nano size. So the drug is inside the capsule or as a core, and then the shell is the polymer. So first, as I mentioned before, to increase the solubility. The second, to increase the stability. Because this is also one of properties that we need to increase at the end is bioavailability. So solubility or dissolution properties increase, stability increase, and then bioavailability increase. So this is the thinking structure of the nanoparticle working in our body, of course. And then with nanoparticle, and then we can make targeted system and everything. So because it's easy to tailor-made, easy to modify it. So because we don't play with the drug, but we just play with the delivery system. So the drug itself is still in their properties. We don't make any combination or any edit. Just we make encapsulated with the drug.
Since you mentioned because engineering these nanoparticles is it's up to us to create the modifications. But also, you also mentioned what interesting to me is that in the point of view of biopharmaceutics or biopharmaceutics classification system, our bottleneck is R2, basically is the solubility, and then after that permeability. Our problem is that a lot of barriers in our body are created, consist of lipids, So if we, for example, create a system that has a good solubility, means that it needs to be polar, because we use a lot of polar solvents, to become suitable for our body. The problem is that if it has a good solubility, then it will become a problem with permeability, because it needs to penetrate the lipid barriers.
Yes.
But if we want to create the system that can penetrate the lipid barriers well, then usually we have the problem with the solubility. So how can we create an optimal?
This is good question, because of course when we deal with human system or in vivo system, it's not that easy or it's not straightforward. Always we compromise with everything. In my experiences is of course solubility and then stability is our target, but we have to know in detail about the target itself. The target itself, when we talk about drug delivery, especially with nanoparticle, is the cell. Okay? Like you mentioned before, the cell have double layer with lipid base, so they doesn't like water. So even we increase the solubility, and then we have a problem with how they absorb, because they have different polarities. But I have a experience to make, or to play around with the charge of the cell. Maybe this is something new, because the membrane of the cell is lipid bilayers. This consists of almost of lipid is negative charge, because they have a COO or something.
Yes.
So the charge of the membrane of the cell is negative charge. So if you want to target the cell, to target the cell, it means we need the particle or something that can attach the cell first, because before you enter the cell, you have to attach first. So because of the negative charge of the cell, we need counter ion. It means we need positive charge of the cell. So we can create nanoparticle with charge, with positive charge. You can combine with another polymer, or polymer that have another charge or positive charge. So it's like counter ion. So we can combine. For example, I'm working a lot with chitosan because it's good properties and have positive charge. So I just combine it with or make nanoparticle with chitosan.
So very biocompatible.
Biocompatible. This is safe or something like that. So we make nanoparticle with positive charge because of the charge of the chitosan, and then when we enter the body or attach the cell, because of positive and negative charge, they will attach to the cell.
Okay.
Because of the touch of the cell, they trigger endocytosis.
Yes.
And then endocytosis, they can absorb the particle inside the cell. So something like that. Of course, a lot of strategy we can use it. We can also add another moieties, for example, antibody, for example. So we can tailor-made the particle or nanoparticle with moieties or with antibody that can attach to the cell with specific cell, for example. So when they attach, and then endocytosis will happen.
Or that's right.
Trigger. So it's something like that. So this is a lot of. But
and I also ever heard that this cytokine, specifically because of this positive charge, it can alter temporarily the T junction.
Yes.
Is that correct?
Kind of. Because chitosan also is. I work a lot with chitosan. I like chitosan very much. It's cheap. Also, we have a lot of source of, because chitosan came from crabs. As long as our sea doesn't dry, we have a lot of crabs, so we can extract it from the sea. And this is good. because of the charge of the cell. Because of the charge of the polymer, because they have a highly charged, positive charge of the cathosan, they can somehow disturb the tight junction.
Yeah. Oh,
it's not
okay.
It's not destroy, but disturb. Disturbs mean like somehow they can open the tight junction because when the cathosan enter the
space between
the cells, because there's a paracellular system. They can the particle or the cathosan can attach the tight junction, and then because of the highly charged, highly positive charge of tight junction, they can somehow open it. Tight junction. I have one publication about it. Maybe we can share it. And when they open it, and then we can enter it. Of course, we cannot destroy because if it's destroyed, everything will enter this,
of course,
and then become
so
dangerous.
not in a permanent manner.
No. We call it disturb, or I don't know. It's like it's not destroy. Destroys in one sense, but disturbs like disturbance, just temporarily.
But of course, we need to make it in a optimum value, right? Because if it's too positive, then it will become toxic to the cell, something like that. So how can we measure this? Is it possible for us now to do in a lab in a daily basis to just, for example, if we already produce nanoparticles, then we want to know the charge of this particle.
Of course, everything that we make have to be characterized. You know,
so
we make nanoparticle. How we prove that our particle is nano? It's like the good question. You cannot see by eyes or by photo or by handy to see this. It's nano. No. We need special machine or special measurement.
So
in this case, we use particle size analyzer. How it works is the same like spectrophotometry. It's like they use laser. So how the machines work is to measure how fast the particle moving. When the particle moving faster, it means smaller, isn't it? It's like Brownian motion. If
because it has a colloidal properties.
Of course, because like I told you before that the particle has its charge. So in one batch of the nanoparticle, they have the same charge. Is that correct? So when the same charge, and then they always moving like this. Like this we call Brownian motion. Smallest particles mean like the charge is higher, is that it? So when the charge is higher, it means the Brownian motion is faster. So opposite with a bigger particle. The bigger particle you have, the small surface that you have you get, it means the charge also getting less. And then the Brownian motion. This is how the machines measure your nanoparticle. Of course, they have a special algorithmic for sure to measure, but how simple that's to measure. We just use like a cuvette, we have put a nanoparticle solution in the cuvette, just put in the machine, they will measure, and then they will with their laser they will measure what it. And also the particle size analyzer, we can also measure the charge. Like I told you, every particle has a charge. Of course, and then the question is also how we maintain, how big charge that we want is possible. We can play around with concentration of the polymer. This is like in detail for sure. We have to have like optimization with concentration of the drug, concentration of the polymer, and etc. etc.
Is it also possible, for example, if we want to do a polymer combination?
Of course, yeah.
Yeah?
Yeah,
So
depend on how you make nanoparticle, because we for example, one of the method that we use is like we call ionic gelation.
Okay, so could you please tell us?
Yeah, we call ionic gelation because ionic.
Okay.
Ionics mean like positive and negative charge. So maybe I will explain some simple.
Maybe for example, yeah.
Yeah, when we have
one that you have
a
already
chamber,
produced.
for example,
Yeah,
chamber, we fill the chamber with water. Okay.
Okay.
Just imagine it is
Yeah.
just like just a sample, and then we take like put fabric. This is the sample of polymer.
Polymers. Okay.
Just
oh,
put
okay.
it,
Yes.
and then with something, and then you can stir it. Okay. There's in chamber. There is water and fabric. Okay. And then you take like balls, tennis ball, the green one. Okay, the green one, and then just put it there, and then stir it again, and then just take the ball. What do you see?
Then I will see the ball with the fabrics around it.
The ball
Attached.
will be
Yeah. Okay. Surrounded,
with the fabric.
Okay.
Because of what? Because of the charge between the ball and the fabric is
in the
opposite.
Yes. Okay. So is it
That's easy. So
how we imagine
yes.
ionic gelation?
Yeah.
Okay.
That's simple. So we don't need a special machine. Just put it together. As long as they have counter ion, positive, negative, or negative to positive, they will attach.
Okay.
So when we want to create nanoparticle with the drug, we have to know for sure. When we want to create everything, we have to characterize everything is fine. So that something simple, that how the drug behave in water, or this polar or non-polar, or how the charge of the, for example, you have a negative charge of the drug. Of course, if you want to make nanoparticle with ionic gelation, you need polymer with positive charge.
Okay.
Or the other way around. Because, for example, negative charge polymers are like alginate, maybe you know it about the alginate, and then carrageenan, for example, and then pectine. Is it some
Just,
because I work a lot with biopolymers, so I just know about it. So.
And there's also a small molecule called tripolyphosphate that
Yeah,
we can use to
we need
walk
to.
yes.
We need sometimes we need to what we call cross-link.
Yeah. Okay.
The polymer, the nanoparticle, to increase the stability.
Okay.
Yeah, with tripolyphosphate is like 3-phosphate with highly charged or negative charge polymer. So we can combine it as long as you know the charge of the polymer or the charge of the drug. You can play around. It's easy, and first you don't need special machine. You and the how you make nanoparticle is just like kun fayakun. What's called kun fayakun? It's just
So be it.
so be it.
Okay.
We don't need anything else.
Yeah, so that's also nice. But actually, I know that you are not only playing with these polymers in the nanotechnology. You are also playing a lot with the lipid-based nanoparticles, like nanoemulsions.
Emulsion, yeah.
Okay, and then I know that you have a product of vitamin D.
Yes.
That it's also based on the nanoemulsion, but it's just pre-emulsified, called the SNETs. Can you please tell us a little bit about that? What's the difference between this lipid-based nanoparticle and the polymer-based nanoparticle?
Okay. Yeah. When it's easy that polymer-based mean with polymer, lipid-based with lipid. So. Basically, usually I divide drug between two. One's water soluble. The second one is lipid soluble.
Okay.
So it's mean like so if you have for example PCS 1 and 3, easy. You just make like polymeric nanoparticle. But if you have drug that doesn't like water or they like lipid, just make it's easy just to make
the lipid base.
Lipid base. It's just because we just put the drug inside the lipid, the oil, and then just easy to make emulsion with.
But if it's lipid based, then will it create a problem with the solubility also later? Because our system is lipid based,
yes.
And then how can it meet water and then it dissolve well then?
Yeah, of course with lipid when we play around with lipid, we need another system, not just lipid. For example, of course we need something that we call surfactant.
Okay.
So because surfactant have two angle to hand polar and non-polar. That's as simple that if you have oil in water and then just put detergent or something to it, then they will be like the shaking, then they will will be dispersed.
But what makes it different between the regular emulsion with the nano emulsions? What makes it different?
Yes, it's just about
technique.
I think it's quite the same, but it's like I told you, it's like in a matter of size.
Okay.
Of course, if we just make, for example, micro emulsion or micro emulsion, is we just need surfactant. But if you want to make the particles smaller, for example, you need something that we call co-surfactant.
Co-surfactant.
Co-surfactant. This is a little bit different between surfactant and co-surfactant. The difference is one of the difference between two is surfactant bigger than co-surfactant. Yes. Okay. Because if you make with emulsion with surfactant, because it's bigger, the size is stuck. They cannot be smaller. So you need something small to make the particle smaller.
Okay.
We can use co-surfactant.
So then it can decrease the surface energy.
Yes.
So that's why then, for example, if you have SNEDs, the pre-emulsified, then only with a very small amount of water inside our body, it can dissolve, like emulsified.
Yes.
Okay, nice. So basically, it's also not really that the solubility is perfect, but it's basically dispersed, but in a very small size.
Very small size.
So then it will not create difficulties in the uptake because it's already.
Yeah.
Okay, then it's really nice to know about these two techniques between the. But based on your experience, because you do a lot of projects related to these nano products. We know that the differentiations between the techniques. We know other type of nanoparticles, like the inorganic nanoparticles, like the gold nanoparticles or carbon nanotubes or something like that. What is your opinion about these other kind of materials?
Yeah. I mean, of course, the two method is good. I mean, like depend on the purpose, of course, and depend the machine that you have. In general, when we talk about how to create nanoparticle, we have two type of nanoparticle. Two type of how to make nanoparticle. First, with milling system, it's like to make a larger particle become small particle.
Yeah.
We call milling, so we crush it.
Yeah.
When you have like, for example, glasses, you want to make it smaller, just crush it, and then it becomes small.
Yeah.
The problem is, if to play until nano size, you need higher energy. So you need special machine, of course. You cannot use your hand to smash it. I mean, like it's like Superman power, but you need special machine. For example, you need homogenizing, but with high pressure. So we call high pressure homogenizer. So with that machine, of course, it's easy. Just put it in the machine with 1,200 psi, the pressure. You can smash it, the particle into nano.
Okay.
But of course, we play around with machines. Okay. Yeah. Of course, if you can earn some money and then you can buy the machines and just put it, nothing wrong. But depend on something that you have. In our laboratory, in our lab, or in our group, we don't use the technique.
Okay.
Because we don't have money to buy that machine, of course. So we use another method we call precipitation. It is like precipitation. For example, it's something that's easy. You can, for example, is curcumin. Curcumin is dissolved in organic solvent.
Yeah.
It's like we can use 70% or let's say 96% or 98%.
Ethanol.
And then you can use, and then first we dissolve in with ethanol, for example, 90%, and then curcumin is dissolved, completely dissolved with the yellow color.
Yes.
And then you can apply titration.
Oh.
Okay, with water, drop by drop, until the composition of the water and ethanol move on. So when you add
then there is a
water,
shift in the percentage of
the
water in ethanol.
drop by drop, until, because when we dissolve, it means the particle. You can not particle, but if curcumin dissolve, it means they dissolve in their molecule. Okay, so you can see. So the color is like clearly, But when you add water more, and then you will find one point that the color become opaque.
Yeah.
When you see something flying, this is nanoparticle. So it is easy.
Yeah.
So you can make nanoparticle with the technique. You don't need something else.
Okay.
So basically, you make something dissolve to disperse.
Yeah. Okay. So it's the other way around with the milling technique.
Yeah, we can use antisolvent, for example, with water, and also we can with anti-pH, for example. Yeah. Because, for example, chitosan have
can dissolve in
6.3 or 6.5. So when the particle, when we dissolve the chitosan, for example, in pH condition, they will completely dissolve, and then you add, you shift the
pH into the more basic level,
nearly the pKa, they will become nanoparticle because they will change clearly to cloudy. This is the simple.
Yes. Nice. You make it quite easy to produce this nanoparticle.
It's nothing difficult with nanoparticle.
But of course, stability is another story, right?
Yeah, of course.
Okay, so I mean, techniques we already know, and then we can imagine, and then I know that you do a lot of this work in your lab, but the question is, because we also have question here from our students, and I think it's also a nice question. Okay, so her name is Melvin. So Melvin is asking how to produce these nanoparticles in a scaling up setup. Because if we want to apply high pressure, for example, if we do this milling, maybe we can just use the ultra-track homogenizer in the lab. But is it also possible to make it in the industrial scale?
Yeah, sure.
Nanoparticles?
Of course, everything is possible, but depend on how you use the method. Which one? I told you before, we have two methods. Bottom up.
Yes.
Or top down.
Yeah.
Top down means you make bigger particle into small particle. You need another machine. for example, you need homogenizing. The problem with homogenizing is, of course, we can use that machine in lab scale easily.
Yeah. But not in the industrial scale.
But because with that machine, we're working with 1,200 psi's, mean like 40 times with our tire pressure, like this is very high. So in the lab, every 2 hours you stop, 3 hours you stop, or after lunch you stop again. But in industrial scale, they will apply almost 24 hours, for example. Because they have its product, they have their line, It is nearly impossible. But of course, some industry make it like that, but it's not easy to maintain because you're working with highly pressurized machines. But with our method, we use bottom up. Like I told you before, we need something that moving, easy, just steer it. So in lab scale, of course, you need steerer, for example, and then upscale a little bit, you need pedals. And maybe if you want bigger one, you need pedals with bigger
size.
Power, bigger size. It's easy. So, in my experience with bottom up method is easy to scale up. So, because when we apply technology and then the technology is not easy to apply. I mean, it's not easy to make a product, of course, because when we're dealing with industry, for example, they don't want invest something new.
Yes.
Because, of course, if you want to ask industry to use our product or to produce our product, they need something that exists in their fabric.
It needs to be that it's already suited to their system, to their line, so then they can just apply it with their machinery.
So easy,
like that.
Make it easy.
Okay, so there's also another type of nanoparticles or nanoencapsulation in pharmaceuticals. If we have this drug with a nice solubility in water, but we want to use the lipid system of nanoparticles, we can use something, or we can produce something called nanoliposomes. What is the difference between this nanoliposome with the nanoemulsion, for example?
Okay.
Because nanoemulsion,
of course. Emulsion and liposome.
Yes.
Emulsion is single layer.
Okay.
So they just have single
of surfactant,
oil, or oil and then surfactant single layer. But when we talk about what's called
nanoliposome,
liposome is double layer.
Okay.
So they use, because liposome the purpose of the scientists form or make liposome is to mimicking the cell.
Okay.
The cell is
because they usually also use phospholipids.
Yes, phospholipid. So they try to mimicking the cell to make to deliver the drug to the cell. So it's like compatibility, they try.
Yes.
So the big difference is like I told you before, the liposome is double layer, and the emulsion is single layer.
Single layer.
Yes.
Okay. So basically, in liposome, we can have something that inside is water in water.
Because depend the drug that you want to use.
Okay, so it depends on the. Okay.
Of course, because if your drug is water soluble, they will load the drug in the center of the liposome. But if your drug is lipid soluble or non-polar, they will enter they will load in the membrane.
Okay.
Yes.
So it's also possible to. Okay.
It's possible. Depend on your drug. But the problem with liposome is quite expensive. I mean, because you use different type of what called
lipids.
Lipid, yeah.
Phospholipids.
Yeah,
Okay.
phospholipid, because it's and also it's really difficult to maintain the stability.
Okay.
Yeah,
But
of course, is
based on your experience, is it possible to create a liposome in the lab?
it's possible.
Is it possible?
It's possible.
It's possible. Just it's more difficult than the.
Yeah, it's more difficult because I don't know, because lipid bilayer is like heavy, it's heavy,
Yeah.
so it's easy to
So then stability is not
precipitate,
good.
yeah.
Okay.
And then the drug load also is difficult, it's less.
Oh,
So it's-
okay.
because how to create the nanoparticle with liposome is not that easy like
Yeah,
emulsion, I mean, like you have to,
But can we characterize the result of the liposome, for example, using the SEM or TEM? Or-
of course.
Or how do we know if
depend
it works
first,
or
of
not?
course, depend on how big your particle first. If it's quite big enough, you can just use a microscope, or
Okay,
if
okay.
if we working with in nano size, we can see with transmitted electron microscope. So it's, how to characterize is the same with every particle. Is quite the same.
Yeah.
Also with
But,
particle size
yeah.
analyzer, and then you can see the graph that show the size distribution, and then you can see exactly the size of your nanoparticle. So.
Yeah. Yeah, well, it's interesting, but of course, it also, as you mentioned before, it depends on the need
Yes,
itself.
depend on
Right?
the need,
If we
yeah.
just you want to deliver the drug in an oral manner,
Yeah.
and then we just need nanoemulsion and it worked well, then why do we
Why
have
not?
to?
Yeah.
Do we have
Make
to
it simple.
liposome?
Life
okay?
is difficult, so
Okay.
why? So make it
But
simple.
what interesting also from the liposome, as scientists said, is that we can decorate the
Yes.
membrane itself, right?
Yeah,
For example, for targeting
Target
purpose,
therapy,
and
yeah,
then we can
yeah.
just put, pegylated
Antibody,
liposome,
pegylated,
things
yeah.
like that, and
Yeah,
then
yeah.
you mentioned also antibody. So then, for example, for intravenous application, then it can be targeted to a cancer cell or something like that. Yeah, well, it's always a nice discussion about this nanotechnology.
This is new technology. I mean, it's not really new actually in the world, but in Indonesia, especially for pharmaceutical technology application, is quite new. So it's very interesting, because if you ask me about what the future of the pharmaceutical technology, I said it's nanotechnology. It's not always like that, but there's no answer.
Yeah, that's right.
I mean, show me the other technology that can answer the problem. For example, with the drug bioavailability, for example, we don't have any answer yet, except of nanotechnology, or we call nano encapsulated technology. This is definitely.
Yeah, what I know that is in the past the regulation really become really aware about this technology, and then they kind of it's very difficult for them to allow these products, this drug product with nanotechnology, but they are now enforced.
Of course, they have to change also. I mean,
study again, and then they really need to, because it's really promising,
Yes,
because
yes. I mean, this technology can answer a lot of things. I mean, of course, I can say it's not the best, but in terms of how big they can solve the problem of the drug, for example, is very promising. Because. Yeah, in my experience, I can make that you mentioned before. I can make some product is the answer of the problem of the drug delivery. For example, I say I have like OSD, a drop, a nanoparticle drop for the children.
Vitamin D, yes.
It's easy. I mean, it can solve the problem of the children delivery system of the drug, because we can drop that vitamin D into anything that consists of water.
Yeah.
So easy, and then I mean the answer can answer the problem. For example, because till now the children or children under 5 doesn't have any dosage form for vitamin D, for example. In the market they just have capsule or tablet or something that is for the adult, for example. So
that's right.
yeah, we can a lot of things. For example, we have a problem. We have a project to make like eye drop also to make to combating with infection.
Yeah.
So we make like mucoadhesive eye drop.
Yeah, because it's polymeric, so it's possible to make it mucoadhesive.
So we can answer a lot of things.
Yeah,
so
nanotechnology. Yeah, I think that's the thing about this nanotechnology, because if we only talk about the size, then nanotechnology is not so special as compared to the molecule.
It's just about the size.
But the problem is that in the molecule, then it will only have these natural properties.
Yeah.
If it is not dissolved well in water, then that's it. That we cannot do anything about the molecules.
Yeah.
Well, for example, one solution is to create new chemical entity.
Yeah,
but it will take like another 10 years.
I mean, and need a lot of money to prove it.
Much easier and faster and more efficient to just.
We're working with the delivery system.
Yeah. So we basically use the same drugs. We just create.
Yeah, just for example, till now, paracetamol is the king.
Yes.
Because I think they found paracetamol is early 70 or something.
Yes.
But now they still use it.
Yes.
So it's the reason, because to create new entity drug is time consuming for sure, and money.
Yes.
So
and based on the regulation, you also have to do another clinical study again, right?
Yeah.
So
of course it's good, but I mean, when we want to make everything easy, just working with drug delivery. So
yes, and then actually now maybe the last part of this segment is about how to make decorations about these nanoparticles. Because what is nice about nanoparticles is that if I imagine it myself, then it's like a vehicle.
Yes.
We can create a motorcycle, or we can create a car, or we can create a small car, and then in the car itself, we can create a GPS, things like that.
Okay.
So how do it work in this nanotechnology in pharmaceuticals? Can we also create the same things like that? Like maybe the GPS to guide these particles into the target?
It's still possible, because the interesting thing when we're working with nanoparticle is, if you want to decorate or tailor-made or to make a targeted system, you don't put it in the drug. Because the drug, if you modify the drug, they will have problem with the activity. That's something that's simple. If, for example, you're working with a drug that non-polar, for example, of course you can make salt with Ka or sodium something. Of course, and then becomes water soluble. But somehow the effect is gone.
Yes.
Because you tailor-made the drug.
The
drug itself. But like you mentioned before, we're working with system, delivery system. We create the bus.
Yes.
So when and the passenger is the drug.
Yeah.
So for example, you need to deliver the passenger to, for example, to Surabaya, for example.
Yeah.
Okay. You don't need to tag or to GPS every single person in the bus.
Yes, of course. Then you can just
modify
the bus.
Modify the bus.
Okay.
So of course, for example, to increase the stability, because between Jogja and Surabaya is a long trip, you know.
Yes.
Maybe we have accident, maybe they have raining, so they need to protect the passenger. Isn't it correct?
Yes, that's right.
Without the bus, every passenger have to maybe use umbrella, use a blanket, maybe to protect sun. They use skincare or everything. So it's not effective. Why we just use the car or the bus and everybody just put it there without any modification?
Yes.
Because just they are.
Yeah, yeah.
We just modified the the bus.
The bus, yeah. If
With
we protect
GPS.
the bus as the whole system,
with
then
the whole
every
system.
passenger will be happy. Yes.
And then we delivered in one bus to the Surabaya.
Yeah, okay.
That's it. So if, for example, Surabaya doesn't like bus with red color, for example. Easy, just painting the bus with green color, so you can enter. But you can imagine if you have to paint every single person without the bus, for example, is it non-effective?
Yeah.
So I think it's like, make it simple. Everything's just, nanoparticle is like, because we working with encapsulated, we don't need modification of the drug. So it's just working with, like I told you before, it's the delivery system.
Yeah. Yeah, since you also mentioned it's as a bus, then we can think about a lot of passengers there, and then we can even create or modify the system for a controlled release, right?
Yeah.
For example, you need to drop 10 passengers in Solo and then another 10 in Ngawi and something like that. And then in Surabaya, it's everyone is ready. So I think then we will have another segment also about that controlled release with someone else. But but I think for this segment, I think it's good enough. And then I think also, since we already talked about the decoration of these nanoparticles, then we know that this nanoparticle is reliable enough if we want to use it to deliver vulnerable chemicals like proteins and nucleic acids.
Okay,
right? And then
it's very sexy.
Yes, so then you also mentioned that we can create these nanoparticles for targeted therapy. So I think for this segment we can
thank
call
you.
it nice, fine, and then after this we will continue to the next segment with the use of this delivery system to deliver these particular compounds like proteins and nucleic acid, and then the use to, for example, treat cancer or things like that. Okay, thank you very much again for this nice discussion. And so I think that's it for this first segment, and we'll meet again for the second segment of the drug delivery system to deliver vaccines, proteins, and nucleic acids. So see you.